Okay, welcome to the next video on doing homework with Maxwell's equations. And this wraps up chapter 2, which is Gauss's law for magnetic fields, which says that the del operator inner product with the magnetic field is equal to 0. And this is from A Student's Guide to Maxwell's Equations by Daniel Flesch. Okay, so here's the only problem worth doing. Determine whether the vector fields given by the following expressions in cylindrical coordinates could be magnetic fields. So it gives you these two equations. And that means we need the uh, divergence in cylindrical coordinates, okay? And he gives you the equation, but I can't live with that. I have to derive it. That's just the way I am. So that's how I learn. So we need del dot A, this vector field, in the coordinates. So here's our transpose equation. Now, the traditional way you would do this at this point is you would write out all of these in terms of the multivariable chain rule, like you learned in vector calculus. I'm going to do it a different way, which I learned in tensor the calculus, which is just to generalize the format of vector calculus. And I learned this from Professor Jim Fowler's YouTube channel called Tensor Calculus, which in my opinion is the best one on YouTube. I'll leave a link to that. I learned an awful lot from that guy. He's very, very good. So imagine if you had just a gradient. So you've got the del operator acting on a scalar field, which is in this format in Cartesian equation, the coordinates. And they said, you need. How would you express this as a tensor equation? Okay. Well, you would do it like this. You would say that this gradient is equal to the covariant derivative of that scalar field times a contravariant basis vector, or conversely, the contravariant derivative times that times a covariant, the basis of vector. Now, if you're unfamiliar with the covariant derivative, it doesn't matter because we're not going to use it. It's just the covariant derivative is the generalized format of the directional derivatives. Because imagine you're in a curvilinear coordinate system, like spherical, the coordinate system, where the basis vectors are changing all over the place. We can't just use the ordinary directional derivatives. You have to account for the fact that they change, and that's what this does. But we're not going to use it. We're going to write it as defined like this. So the contravariant derivative of this scalar field times this basis vector can be expressed as the metric tensor times the directional derivative of that with a generalized the coordinate times this basis vector, okay? So we can express that whole thing like this. So where we've got the elements of the tensor, and there's only 3 of them we need because all of the off diagonal ones are 0. So R phi and RZ and phi Z and etc. They're all 0. There's only 3 non-zero elements of the tensor, okay? So we can immediately start finding our metric tensor components. Now, if we have a displacement vector, a position vector, it has an x component, y component, z component, and we know what our transpose equations are. There are these, and you know these. So we put those in here like this, and now we can actually find our basis vectors that we need, which are these, by taking the partial derivative. The partial derivative of a position vector with respect to a coordinate is actually the definition of a basis vector. This is what it is. So if I do it with respect to r, I get the ER basis vectors. All I have to do is take the partial derivative of this with respect to r. And so this is a constant, this is a constant, derivative of r is 1, the derivative of this is 0, so we get that. Okay, now we can immediately find the component that we need, which is GRR is defined as the dot product of ER dot ER. And that's just this squared, which is 1, cosine squared theta plus sine squared theta equal 1. Okay, and later on we're going to need our unit basis vectors, and you find those by taking your basis vector, divide it by the magnitude of that, which is so this expression divided by this expression squared, and then you take the square root of it, and that's the magnitude of ER. And this is just 1, so 1 squared is 1, and the square root of 1 is 1. So the ER hat basis vector is the same as the ER. Okay? Now we got to do E theta, which is the exact same thing. We take the partial derivative of this with respect to, I keep saying theta, I mean phi. I'm sorry. All right, and we get this. The derivative of cosine is minus sine. R is a constant. Sine is cosine. R is a constant. Derivative of this is 0. Once again, we find our element of the metric, the tensor, E phi dot E phi. So this is r squared sine squared theta, r squared cosine squared theta. You factor out an r squared, sine squared theta plus cosine squared theta is equal to 1, so you're just left with r squared. Once again, we need to find our unit, the basis vector E phi. To do it the same way. And so this becomes r squared. Square root of r squared is r. It takes these r's out, so that's what's left. So the difference between E phi hat and E phi is just r. So we're going to need this later, okay? I've got one more to do, which is EZ, and that one's easy because everything's 1, right? The derivative of this with respect to z is 1, everything else is 0, and 1.1 is 1, etc. It's all 1. It's easy. Okay, so now we have our metric tensor, but remember in our equation we needed the contravariant metric tensor, which is the inverse metric tensor. Now, taking the inverse of this is easy because all of the off-diagonal elements are 0, right? So we just put all these under 1, and it's that easy. That's all we do. So now we can actually write this whole expression out. We now have these components. So GRR is 1, G phi phi is 1 over r squared, and GZZ is 1. Okay, so, and now we need to change these to their unit basis vectors, because the problem he gave had unit the basis vectors in it, so we have to do the same thing. So the only difference is these are the same and these are the same, but the difference here is r. So that'd be r times this, takes out one of those r's, so we're left with this. Now, if we just take out the f out of that equation, this is the del operator in cylindrical coordinates. And I think that was a very fast and easy way to do it compared to the way I would have done it had I not thought of this, by doing the multivariable chain rule, which is just a buttload of algebra. Okay? So we have this expression. Now we have a vector field with AR, A phi, and AZ components and these unit vectors. So we need to find the divergence of this. And how do we do that? We dot them. Now, the trick here is this is a product. So every time we take a partial derivative inside here, we have to use the product rule. First times derivative of the second plus the second times derivative of the first. We have to do that for every one of these for these 3 times, okay? Now let's look at our little drawing here. He calls that, most people call this rho. For some reason, he calls it r as opposed to r being this. I don't know why, but he does. So we have to follow what he does. So he's got the unit vectors here, r hat, phi hat, and z hat. And the reason I'm pointing this out, because a couple of times we're going to be taking partial derivatives of unit vectors, and 2 of them are special, and it's these 2. Okay, the partial derivative of r hat with respect to phi, this is r hat, we found that above, right, is this expression, which is just phi hat. And the partial derivative of phi hat with respect to phi is this expression, which you see is the negative of this, is r hat. So these 2 are special, and the others are all 0. So we need to know that first. Okay, so I'm just going to take one piece of this at a time because it's extremely long. Excuse me. All right, so I'm going to do the first one. I'm going to write it out in total, and then the next time we'll do it in our head. All right, so I'm going to bring out the r hat from here and our dot. And then so we're going to take the first times derivative of the second, so it's AR this, plus the second, which is r hat, times derivative of the first. Going to do the same thing here. We get 2 terms Do the same thing here. We get two more terms. Okay. Now let's look at these. So the partial of r hat with respect to r is 0. So this goes. Here we've got this stays, and r hat dot r hat is 1. So this one stays. Okay. The partial of phi hat with respect to r is one of our special ones. Where'd that go? There it is. No, it's not. It's r hat with respect to phi. All right. So that's 0, but it would be 0 anyway because r hat dot. No, never mind. It's 0. This one's 0. R hat dot phi hat, they're orthogonal. Remember the picture? So that's 0. Here we have the partial of z hat, that's 0. And here we have r hat dot z hat is 0. So there's only one term that survives, which is this. Okay, let's take the next piece, which is this. So I pulled out 1 over r phi hat here, dot. Okay, now think about this. So the first times derivative of the second, which is the partial of r hat with respect to phi, is 0. And then the second times the derivative of the first is r hat with respect to phi, which is this one. So it's phi hat. So we put that in. Now in this term, the first times derivative of the second, so the partial of phi hat with respect to phi is 0. So then the second phi hat times derivative of the first is this, and that's going to stay, right? Because phi hat dot phi hat is 1. All right. So we can complete this now. So we got phi hat dot phi hat is 1, phi hat dot phi hat is 1. So we got AR over 1 over R here. And we got 1 over R times this expression. So there's another one that stays. And then the last one is everything goes to 0 except the very last term, which is z hat dot z hat is 1. And we get this. So now we can take these 1, 2, and 3 and put them together. And here's what we got is the del operator inner product with a vector, the field is equal to this. Now you could use it like this, but that's not the format they want. That's not the one he gave. It's not the one they use anywhere. And I must admit, full disclosure, it took me a while to figure this out. And once you see it, it's just like, I laughed at myself. It's so simple. If you take this expression, 1 over r times the partial of r with respect to r, this is once again, a product rule, right? So you got 1 over r times the derivative of partial of ar over r plus 1 over r, the second times derivative of the first. Well, this is 1. So you just get AR over R. And this cancels to 1. So it turns out to be this. So this right here is the same as this. And this is what they want. So you write it like this. Okay? So this is the divergence in cylindrical coordinates. So now we can do our problem. Okay, so here's the problem he gave, A and B, with these functions. So we just take the divergence of that. And now remember, this is just the AR part that he's given. We don't need all the rest of it because he didn't give us any more. He just gave us R hat, the part. So this is the AR part. And we solve this. And you see that once these R's they cancel, it's 0. So yes, it could be a magnetic field. And the next one is the same thing, but over R squared. So that leaves 1 over R. And then you take the partial of this. And you get a negative 1 over r squared here, right? So I've got 1 over r. So I'll take the derivative of that, 1 over r squared, and pick up a negative because it's in the denominator. And then I get this expression, so no, it can't be. So that was kind of anticlimactic compared to what we went through, but it was a lot of fun, and I learned a lot. I hope you did. I'll see you later.